Welcome to another physics tutorial. Today we'll be looking at a mechanical system that involves moving a mass linearly across a plane with an inclined force. And now this type of motion is very simple in theory but a little complex in practice, so we're going to analyze how to do that, and we're going to be looking at equations of motion and also analyzing frictional forces in respect to threshold threshold movement as well. So let's jump right into the problem. A 68 kilogram crate is dragged across the floor by pulling a rope attached to the crate and inclined 15 degrees above the horizontal. Part A asks, if the coefficient of static friction is 0.48, what minimum force magnitude is required from the rope to start the crate movement? So before we jump into part A, let's just take a look at this free body diagram that I've drawn here, and let's complete it a little bit. That way we give ourselves a better picture of what we're trying to do here. So if this is the mass m right here, we can deduce that this force here is the normal force, and this is the gravitational force as well. Pretty straightforward. We can also deduce that this is a 15-degree angle above the horizontal, and that this is the tension force pulling the rope at this angle. Now we can divide this tension force into angular components, this being t sine theta, and this being t cosine theta. And then we can also draw the frictional force here. This is the static friction force, which acts against the object as it moves this way. So now we can jump into part A, now that we have a good baseline about our free body diagram. So part A is asking, if the coefficient of static friction is 0.48, what minimum force magnitude is required from the rope to start the crate moving? So first let's draw out the equations of motion for both the x and y components of the system. So let me change the color here, and so for the x component, what we have is we've got t cosine theta minus the frictional force Fs is equal to 0. And I should note that this would normally be equal to F net, but in this system, we are examining it at a point where what we're trying to solve here is essentially when the static friction force normalizes the forces on the other side and vice versa for the y components. This is the threshold potential of the system, and this for the forces that we're solving for, this is going to be the force where the system starts to move. So we can label that F net as 0. So this is the x component, and let me change it, and we can do the y, and here's the y. And for y, we've got a t sine theta plus the normal force, because they're both in the positive direction, minus Fg is equal to 0 again. Alright, so now we've got the equations of motion, and now what we can do is we can simplify this a little further, and let's first think about what condition this system would need to stay at rest. So for this system to stay at rest, analyzing the x component, what we get, and in conjunction with the y component, what we get is that, and I'll do a little simplification along the way, so let me just write this out. To stay at rest, the system needs t cosine of theta to be less than, and now I'm substituting in the following, and before I write this, let me just make a note of this in case you didn't know. Fs is equal to mu s Fn, and that's the, and just a reminder that Fg is equal to mg, where let's just note that g is equal to 9.8. All right, perfect. So now we have, oh, I'm sorry, there should not be this equal to. It should just be that t cosine of theta is less than the coefficient of static friction times mg minus t sine theta. And this equation is derived from algebraic manipulation of these, where set them equal and then solve for like as so. So this is the condition for the system to stay at rest. But what we are more interested in is when the system is moving. So when the system is moving, to move, we need the forces on the left, the friction, basically, essentially, we need the frictional force to equal this force from the tension. So that way it begins to move. So it's simply rewritten as t cosine of theta is equal to the static frictional coefficient times mg minus t sine of theta. All right. And so now what we can do is we can simply solve this system for t. So via algebraic manipulation, what we get from deriving this equation is we get t equals mu s mg divided by the cosine of theta plus mu s sine of theta. And then what this yields is t is equal to 0.48 times the mass 68 times gravity 9.8 divided by the cosine of 15 plus 0.48 times the sine of 15. And let me just extend this a little. And this yields, evaluating it, approximately t is about 293 newtons. And that is the approximate value of the tension force on this rope. All right, so now let's take a look at part B. And then we'll do part B right over here. So part B asks if mu k is equal to 0.33, the coefficient of kinetic friction, what is the magnitude of the initial acceleration of the crate? So in this situation, we no longer have 0 here. What we have is that, and I'll write this out once more. We have that x is equal to t cosine of theta minus, this is fk because now it's frictional, kinetic friction, is equal to mass times acceleration because we need to derive the acceleration, and then we get y is the normal force plus t sine of theta minus mg is equal to 0. And the reason it's 0 is because there's no movement in the y direction. We just want x movement. And so what we can do is we can continue to derive this once again, and what we yield is t cosine of theta minus mu k with substitution times mg minus t sine theta, just like over here in this component, is equal to mass times acceleration. All right, and solving for a in this instance, what we get is, and I'll draw a little arrow, we get that a is equal to, oops, that's bad, a is equal to t cosine of theta I'm sorry, it's t cosine of theta plus mu k sine of theta divided by the mass of the system minus mu k times gravity. And so evaluating this at our values, we have acceleration is equal to 293, the tension force, times the cosine of 15, plus we have the coefficient of kinetic friction at 0.33 times the sine of 15 divided by the mass, 68 kilograms, minus 0.33 times, that's 9.8. And this, I'll just draw an arrow up here. Evaluating this on the calculator, let me just quickly do the calculation. 1 second. Let me quickly do this. It's minus 0.33 times it. All right, and evaluating that, we get an acceleration value of approximately 1.3 meters per second squared. And this is the initial acceleration of the crate with that coefficient of kinetic friction. So thanks so much. I hope you enjoyed this video, and I hope it was very helpful, and hope to see you next time. Enjoy.